So I am a research physicist for the Air Force Research Lab, specializing in quantum algorithms, which is what I'll be talking to you guys today. Perfect talk to follow because I love that the scope of that last algorithm was more long-term focused. The benefits really kick in when the computers kick in, and so will this one. So I have the pleasure also to talk about my coworker's research, Sahil Patel, who could not be here today. But he is leading the quantum machine learning effort for us, and he's had some great results using autoencoders, which are basically the equivalent of classical autoencoders that take data and compress it. And so the idea of compressing quantum data is pretty interesting, because if you have 5 qubits and you only want to send 2 through a quantum network, for example, you can use a parameterized quantum circuit to compress data down, and it is, very advantageous to save on resources. So the premise of it is very much the same of classical autoencoders. You sort of have this latent space, you train your data, and then ultimately the output is essentially a smaller quantum state. And what's interesting, and I'll point your eyes to, is that on the right-hand side in the blue, you know you've compressed your data when you can confirm through experiments and measurements that one of your qubits or multiple of your qubits are in the 0 state. So that means they're essentially pulled out of a tensor product. And that means you know that the remaining information is stored in the remainder of the qubits, and you can throw out that 0 state. So if you want to come talk to me afterwards about our quantum machine learning efforts, I'm happy to field questions on his behalf. And so with that, I'll get into my own research. I was happy to present here last year, and I'm happy to be here again because I have some fantastic new results to show you guys. And so I'll just start with the recent publication that we had from last year's talk, which was Gaussian amplitude amplification for quantum pathfinding. And so we were very happy to stumble upon this result, to use amplitude amplification in a new way, and we weren't the only ones. So this was very reassuring that 2 simultaneous papers came out that were exploring the same idea, which is to switch up the oracle in Grover's to now solve a combinatorial problem. Or in a case of the Fermilab, they were doing a quantum phase estimation type problem. And so I'll start with this very high-level question. This is where we started the research project ourselves. And so can we use amplitude amplification, which is a very well-known algorithm, to do something different? In this case, solve optimization problems, because that's my particular interest and my specialty. And I'll say yes. The paper that I just showed you is sort of the first proof of principle, and I'm very confident to say that with other people's results, it is absolutely possible. And so this is a new way to solve the same types of problems that you might otherwise solve on QAOA or parameterized circuits or something along those lines. But it is not without its own challenges. And so this is my day-to-day job. I have to ask myself the real questions, which is it NISQ friendly? What's the gate count? Is it a speed up? What kind of problems would an experimenter have? How applicable is it? And so those are the results that I've spent the last year trying to trace down, and I'm happy to share with you guys. So I will start here. In my own head, when I think about Grover's algorithm and the amplitude amplification that we do, I sort of make this analogy. Although it's not a strict math analogy, it works very, very well, which is to say that Grover's algorithm, the one that we learn and know, is the sort of optimal case. It is the upper limit of what amplitude amplification has to offer, and you'll see that in a few slides. And so in my mind, I equate that to a delta function, which is to say that the mark state you're looking for is special, and everybody else is not special. Now, it's obviously not a delta function in the pure math sense, but you can kind of see what I mean here, where there's 2 things. You're either yes or no, and that's very much what a delta function does. So why is that relevant? Well, there's another known math result, which is that the delta function is very, very closely related to Gaussian function. In fact, in the limit, where a Gaussian function, you squeeze it down to essentially infinite, and a small point, it becomes the delta function. So now I want you to think backwards. If Grover's algorithm is the limit, the delta function, we can relax it. And if we relax Grover's algorithm, we get more problems. We get a Gaussian distribution of answers, and that is sort of the basis of this research, where we get to sort of look at, okay, what's a more interesting problem, and what are we going to sacrifice by moving away from the perfect limit of Grover's? And that was actually one of the very first things we did, which was to say, okay, let's swap out that oracle for a Gaussian now, and let's compare. Do probabilities still reach what they did with Grover's? If not, how good are they? And so this is a result from the first paper, and you can just see it. Grover's algorithm on a discrete machine, because again, these are gate-based, so everything has to have a cutoff. We can't really go to infinity. Grover's is sitting there at the limit. It is the best you can do. But along that black line at the top, those are pretty good probabilities. You know, if you can swap out a database search problem for what I'm going to show, which is combinatorial optimization, and still get a 90% probability, you'd probably take that. So, just to kind of give you guys the flavor of, you know, why this is not a trivial problem, I have an animation here that's going to show you amplitude amplification. So what you're going to see is the complex plane. And what you're going to see is the red dot. That is the solution. And this could be, say, a weighted max cut or any of the other flavor of those algorithms. And it's a little bit crazy, which is why, you know, it's a non-trivial thing to study this. So as you're watching this, it's going to speed up because Grover's takes a while. It's going to need a couple thousand iterations or so. Watch the red dot and watch the scale of the axis. And for numerics, I've put the probability of the optimal solution at all times, along with the step count. Now, for warning, if you're sensitive to dizzying things, look away. I'll give you something else to look at, which is the probability comparison. So while my amplitude amplification is going on and the complex plane is having a field day spinning around, these are the probabilities that we sort of come to expect. So Grover's algorithm, to no one's surprise, is the optimal and it is the fastest. It reaches the highest probability, does it the fastest, and that's what we've come to know. There are 8 nines in that probability percent, and that's fantastic. That's sort of the goal of quantum. But now I ask you, do you need 8 nines to be dangerous, to solve real-world problems? No. You'll probably take a slight hit in probability if you're going to solve something more interesting, like a finance problem or a logistics supply chain problem. And so now it's stopped. The probability is 85%. It's still there in the complex plane. And in order for that one point to be there, everybody else has to be clustered in the middle. And so I'll finish this with saying that what you saw, we do not yet have a clear analytical math definition for, so, you know, it's still an open question. We just simulate it, and we simulate it again and again and again, and it always works. So we're pretty confident that it's a feature, not a bug, but we're still trying to track down some more math results for this. Okay, so now let's get into an actual real problem. Across quantum computing and just computer science in general, a lot of people point to QUBO as sort of a toy model that everyone can relate to. You know, everybody's real problems are not QUBOs in the real world. They have constraints. They're much harder. But if you can prove something on QUBO, that's a great start, because then everybody can relate back to you and say, well, my problem's different in this way, and so I just need these constraints. So just for everyone's definition, what do I mean by QUBO, and why is it good for quantum? Well, it stands for this acronym, Quadratic Unconstrained Binary Optimization. So how does that play into quantum? Well, the quadratic means we only need 2-qubit interactions. The only gates that we need then to build this are 2-qubit gates. That's pretty nice. Unconstrained means the full 2 to the n space. When you go to constrained, that means some solutions are not allowed. That's much, much harder, and that's where the research is going. But we're happy with what we've got here. And finally, binary, these are discrete machines. You make a measurement at the end of the day, it's all zeros and ones. So those zeros and ones better have some important meaning. They better actually have a solution to your problem. Okay. So to give you another concrete example, this is sort of what we've been testing on. It's a very simple case of QUBO. It's linear. And here's the cost function at the top that we're trying to evaluate, and we're trying to get a solution out of quantum. So it has first a weighted problem, or a weighted component on singular nodes, like you see here. And so if a node is in the 1 state, you add the weight to the cost function. If it's in the 0 state, you don't. Similarly, there are weights between nodes. So when 2 nodes are on, as in they are in the 1 state next to each other, then you add their weight to the cost function. If one is in 0 and one is in 1, you don't. So this is the pretty standard model of QUBO, and it's pretty easy to build. And so what we've sort of come to talk about it amongst ourselves is we call it a cost oracle, because what you're going to get out of Grover's now is the value of a cost function, but you're encoding it in the traditional oracle component. And the diffusion part of Grover's, I'll say we don't touch that. That's the same as it's been for 20 years now. Okay, so what does quantum do here? So we need to mimic this cost function, but we only have gates that we're all familiar with. So first and foremost, how do I encode the weights of individual nodes? Well, I need something that's going to affect a quantum state only when it's in the one state. That's the traditional phase gate. It applies a fate when you're in the one, and if you're in the zero state, it does nothing. That's exactly what I need for my cost function. Similarly, what do I need when two nodes are next to each other in the one state? I need the 2-qubit phase. Because only in the case when they're both one do I want to pick up a phase to correspond to this weighted value, and when either of one of them is off, you just get a 0. So these are the native gates that we build our oracle with. Come find me afterwards and I'll show you all the tips and tricks of how to do different oracles, but here it is. So this is what an actual oracle circuit would look like. It's pretty shallow depth circuit, which is great. The circuit depth of your oracle is directly related to how many interconnections you have in your QUBO. And so what do we get? Well, we're using phase. And I always tell my coworkers and all the hardware team that phase is the secret sauce of success for quantum. It is the fundamentally non-classical part that we're trying to exploit. And so if I put the raw numbers of a QUBO into phases, mathematically I get out all the answers in phases. I get the best answer and I get the worst answer in this e to the I theta form. But obviously there's a problem here. What does it mean to have a 77, which is in radians, of course, so e to the I 77? That's no good. The only thing that matters are values between 0 and 2 pi. That's the only way that things can be unique, and so that's a problem. And then number 2, obviously, probabilities are only reflective of amplitude, magnitude. So if I put these phases in and I've encoded my problem, that's fantastic, but I need to measure these. And that is sort of what Grover solved. So number 1, you can solve the scaling problem. You can just shrink down your problem, and that's a lot of the research I do, and a lot of the extra results I couldn't fit in today's talk are about this scaling vector. And then the diffusion operator, the mechanism by which probabilities grow iteratively. Okay. So I want to jump ahead to the fun results that we have, which is we've done a lot of research into that scaling factor and how it really unlocks an optimization problem. If you know it, you can jump straight to the answer, and in principle, you can solve any optimization problem you can encode first try, just like Grover's. But the reality is it is a hard constant to find, and you are limited by measurements. And so, that is a major, major hurdle that we've been trying to solve. I'll just note on the side that why this works has to do with the underlying distribution of your problem. This was the result that was confirmed by the Keio University with Rod Van Meter's group, which is to say that there are other types of distributions that can be exploited, where essentially you're leveraging all of the wrong answers, that's the central cluster of the Gaussian, into a mean point, which you can use for reflections about the average. So you're using bad answers to make the good answer pop up, which I think is really fitting for quantum. Okay, here it is in more detail. So what about a Gaussian is special? Well, number 1, Gaussians appear all the time in combinatorial optimization. If you don't have sort of any notion of the weights in your problem, chances are you'll have something like a Gaussian where a lot of the answers will cluster in one region, and that's what's good. Even better is we want the best, either the minimum or the maximum. So what that means is we're always looking for the solutions on the tails of the Gaussian. Or maybe we want a heuristic answer. That works too. I've been told by fellow colleagues that, yeah, in real computer science, we don't really always want the best solution. That's nice when you get it, but if you're controlling a chemical plant and you need answers in real time, we will take what's, within the 1 or 2%. That is totally acceptable. And that's what led this research and sort of inspired us. I will say you can't get solutions in the middle of the Gaussian for the reasons that I just explained. It's too dense. There's no mechanism by which you can reflect and grow the amplitudes for these states. So you're limited, in a sense, to finding answers on the tails but that's okay. That's where all the good answers are anyway. Okay, what else is good? Well, a Gaussian, as I showed in the first slide, it has this feature where there is so much concentration in one area, and it's physically separated in this distribution space from the answers you want to find. So that's what you leverage to your advantage. And of course, the tighter the Gaussian, the more it approaches that Grover limit that I described, where you're kind of like a delta function, the better you do. The higher the probabilities, the better the chance. So everything about a small sigma Gaussian is good, but what we've come to learn is you're just fine with almost any size. Okay. So what we do in our research is we're trying to understand better how we can convert a problem, any order of magnitude, whether you're solving small numbers, large numbers, finance, logistics, doesn't matter. You take those numbers, and it always turns out that there's a single parameter you need, which we've called PS for phase scaling. And it's always related to the problem itself. So the order of magnitude is pretty always well known. You always want to start searching for this one parameter as it relates to your min and max of your problem. Well, why is that challenging? If you knew those values, you wouldn't be trying to solve this optimization problem in the first place. So there's a catch-22 here where the information you need to unlock Grovers is actually the information you're just trying to solve anyway. However, with recent results, we've shown that sampling is effective, estimation methods are effective, so you can get a starting value to PS using very cheap classical tricks that almost cost you nothing in terms of computational complexity. And so what you're seeing on this picture is the problem, and what you're seeing on the right is the oracle. So it takes the problem and it puts it into an oracle in the complex plane. And then that red X is the mean point, the blue point is the optimal solution, and so it's going to reflect. And each iteration, it reflects a little bit further and further until it reaches those nice probabilities we want. Okay, so now here comes the fun ones, and I'll speed through these, so find me afterwards if you want them again. But we're investigating a hybrid model because we've now come to appreciate that a classical computer is going to be the way that's going to solve the part of it that we can't do quantum. As in, we can only use the QPU for what it's good for, the amplitude amplification. But then once we get that measurement, that's information for the classical computer to use, no different than a QAOA parameterized quantum circuit does in a gradient descent. And so the interplay of the two is really promising because once a classical computer is brought into our algorithm, we kind of get the sense we're on the right track. Because now we're using classical for what it's good for, and we're using quantum for what it's good for. And so I want to skip ahead here. Yep, here we go. One thing we were really, really curious was if the optimal solution is going to get all this, great probability of success, what about the lesser ones? And where do they lie? And is there any correlation to where the second, third, fifth, 10th best solution might lie? Well, turns out they're incredibly related to each other, and this is what we're now taking advantage of, which is to say, these are the best 50 solutions. And I'm sure everyone here is going, that's a line. Yep. So the best 50 solutions fall on a line. That means you can use this line to your advantage. This is sort of like a fundamental part of what quantum is offering you. And even better, it's sort of independent if there are holes in the problem. As in, if a solution exists or it doesn't exist, that's fine. Quantum doesn't care. The manner in which the solutions are distributing themselves in this particular diagram, which is solutions versus the phase scale, it's in a line. But it's not really a line. Nor should it be, because these are Gaussians undergoing some crazy process, so why would it be linear? And it's not, but it's approximately linear, and if it's that approximately linear, use it. Just pretend it's a line, because it's going to functionally work in a real algorithm. So this is the red box that I just showed you down there in the corner that looked like a line, but then when you blow it up, it's obviously not. And so this is sort of the idea that sprung on us, which is to say, wow, if this is true of all the optimization problems, all I need to do is to sort of get close enough. And I can get close enough through sampling, that's totally reasonable, as long as I don't overshoot into this region where amplitude amplification is now kind of just spinning out of control, meaningless answers, noise practically. So if I can get close enough, I can do some samples, I can make some measurements, I can create an approximation for this line, and in theory, it will lead me directly to the optimal solution I want, if a heuristic isn't good enough. If heuristic is good enough, then, stop where it's appropriate. Okay, so this is my favorite slide. So this took a lot of computing power on my laptop to produce this, but what you're going to see is two side-by-side videos. On the right are probability. So it's a bar chart where you're going to see individual probabilities pop up and down for individual solutions. The top 50 solutions, by the way, and this is a minimum problem. And then on the left, you're going to see the under-the-hood view. You're going to see individual quantum states as they come into probability and then fade away. So everybody gets their turn, more or less. The 50th best all the way to the minimum best get their turn. So here's what it looks like. So in a lab, you would scan through this PS space, and this is what you would see. As you incrementally decrease PS, one by one by one by one, you find the solutions to your optimization problem. And sometimes they're good, sometimes they're bad. When you get far enough away from the optimal solution, they're really clustered. But now, as you can see, once you hone in on the best answer, it's a little more sparse. And you get these little peaks and valleys, and they're not near any of their neighbors. And that's what's difficult. And so the strategy is to start somewhere with a high density of states and a high density of solutions. So now I'm running out of time, so I'm going to speed through this, but this is the model we're investigating, this hybrid algorithm where we're using a classical computer to steer the quantum, and we're letting quantum do what it does best, which is amplitude amplification, and we're letting classical do what it does best, which is these higher control logics to steer it. And then what would it look like experimentally? So if you just went to the lab and you just relied on quantum measurements, could this actually work? Those probabilities seem nice, but what would an experimenter see? So this is a sort of an animation that will show you what an experimenter might see based on those probabilities. Each black dot is an individual measurement where you performed the full Grover iteration. And so you're already probably seeing the trend. There's a visible line that is pointing you to the solution. So you go and you go and you go and you evaluate your cost function, and each one is smaller than the last, and it's leading you straight to the optimal solution. But how do you know you're done? This seems kind of like a lot of other variational approaches where you don't know if you hit a minimum. Oh, but quantum already helped you out there. Once you go too far, you return to noise. So there's almost this self-check system for quantum, which I think is really, really special and powerful. The fact that you can sort of confirm experimentally if you've hit a local minimum or the true ground minimum of an optimization problem. So with that, I do want to skip ahead because I don't want to cut too much time into the next speaker, but we're doing a lot of this, and we're trying to use the same language that other people will understand so that we can sort of relate this to real-world problems. And so if your problem looks like any of these well-known classes of problems, well, then we're in business, because the oracles that we can build are all more or less the same, but how you use it strategically can answer completely different problems. So that's it for me.